Okay, hey all. This is our first video dealing with Chapter 14. We're looking at properties of solutions. Chapter 12 covered gases. Chapter 13 covered a majority of 13 covered liquids. A very small amount of solids that we have to worry about. So now we're kind of putting that all together and looking at solutions, right? What happens when we start mixing all these different states of matter together, okay? The first thing I want to tell you guys is to review solutions from Chapter 5. We discussed a little bit about solutions back in Chapter 5. We did some molarity calculations back in Chapter 5. That's kind of like one of the main things you want to worry about when reviewing is just your molarity calculations. If you're confident with those, great, you should be fine. There's a few vocabulary terms like solute, solvent, solution, things like that that get used a lot in this chapter, lots of S words, so you want to make sure you're familiar with all those terms. So if you need to, look back at our Chapter 5 stuff about solutions, not the entirety of Chapter 5, just the solution part. Okay, well, let's dive in. So let's talk about solutions. Okay. Quick definition. Solution is, solution is homogeneous. Okay. Has to be a homogeneous mixture of two or more substances. Homogeneous meaning looks the same, right? Evenly mixed. That's a solution. If it's not evenly mixed, it's not considered a solution. If it's heterogeneous, it's not considered a solution. Okay, there's other terms for that. We really don't have to worry about those at all. We really want to focus on solutions, so it has to be some homogeneous. One thing you definitely want to take note, a solution can be made up of gases, liquids. Actually, I'm going to write and or solids. It can be a combination of any and all of these things, right? We tend to think of solutions as just liquids. We tend to think of it as only liquids, right? Or solids dissolved in a liquid. Yes, that makes up most solutions that we have to worry about, but technically it could be a mixture of any of these things. Gases, for example, hey, the air that you're breathing, right? Air is a mixture of multiple different gases, and it's homogeneous because they're all evenly spread apart. That's a solution made up of oxygen, nitrogen, carbon dioxide, argon, things like that. You could have gases dissolved in liquids. Hey, soda, my favorite, CO2, which is a gas, dissolved in water, which is your liquid. You could have two liquids mixed together, say water and alcohol, right? That makes up a homogeneous solution. Okay, your typical solid in a liquid, heck, pick any ionic solid you want to. Table salt gets used a lot as an example. Table salt's a solid, you dissolve that into a liquid, hey, you've got your solution. You could also have two different solids mixed together. Look down at any jewelry that you're wearing. That's not just one metal, that's a multitude of metals, right, all put together to make them stronger and less reactive with your skin and the air and stuff like that. Gold is a mixture of multiple different metals. The gold that you wear is a mixture of multiple different metals. Okay, steel, right? Steel is not just one element; it's a mixture of different metals. So those are examples of solutions. They all look the same throughout the entire solution, but it's made up of multiple pieces. Okay, so just kind of keep that in mind that you can have lots of different kinds of solutions. I want you guys to be aware of that. So to kind of stress that homogeneous idea, substances disperse uniformly through each other. Uniformly meaning evenly. And the last thing to take note, back from our Chapter 13, intermolecular forces occur between our solute and our solvent. So intermolecular forces, guys, from last chapter, you really want to be confident with those. We use them a lot to explain the solution behavior in this chapter. So if you need to, go back and review intermolecular forces. Search all sorts of other resources, other videos. Look them up online. You can find pages upon pages. You can find PowerPoints on this stuff. Get as much as you can about intermolecular forces if you're still having trouble with them. Okay, let's move on. Okay. Solutions. Ugh, that doesn't look like solutions. Yeah, that's pretty good. Ugh, that's an N. Oh, I'm making it worse. Okay, anyway, it says solutions. Solutions form when we have attractive forces between our solute and solvent. Wait, solutions form when attractive forces between solute and solvent are comparable in strength with those forces that exist between our solutes and our solvents. Oops. Or solvent themselves. Okay, let's kind of discuss this idea. It's kind of a big one. We'll go into more detail about what it means here in a moment, but I want to relate it to the image I've got going on up here. Okay, so solutions form when attractive forces between solute and solvent are comparable in strength with those forces that exist between just the solutes and just the solvents. Okay, so if we take a look at here, the image here describing salt, NaCl, dissolving in water. Okay, so here we have our salt crystal, right? It's like a cube, repeating sodium and chloride ions. And it's going to be mixing, hence the addition sign, with H2O. Here's our little tiny water molecules, right? It might be difficult to see, but you have your oxygens, your red oxygens, your black hydrogens, and the partial positive and the partial negatives. And when these two substances mix, they form a solution, right? The salt dissolves. It breaks apart. All the ions then spread out. If we take this, look at the intermolecular forces between each one of them, here in our salt crystal, it's made up of ions. So the force involved here is an ionic force. It's an ionic compound, right? Just ionic. And we're mixing it with water, which has hydrogen bonding, right? It's a dipole-dipole hydrogen bond. Hydrogen bonding being the specific dipole-dipole interaction, right? So very strong hydrogen bonding. When these two things mix, we now have ion dipole IMF forces, or I just said forces twice, intermolecular forces. Right, we have our ions, sodiums, and our chlorides, and they're interacting with a polar molecule, hence ion dipole. All right, all these are very, very strong forces. They're pretty comparable. Okay, we have ionic, which is our strongest force, mixing with hydrogen bonding, a pretty darn strong force, and we're making ion dipole, the force right in between the two of them, a pretty darn strong attraction force between our sodium and our polar water. So when everything is kind of comparable, the solution forms. Okay, if the forces are so different, those solutions tend not to form. Hypothetically speaking, if I was trying to take table salt, ionic, and trying to mix it with, let's say, a liquid whose only intermolecular force was dispersion forces, the weakest one, guess what? Not going to happen. The salt will not dissolve in something that has dispersion forces. Go ahead and try and dissolve salt into something like oil. Okay, doesn't really happen too much. Oil is very, very non-polar, so it's only made up of dispersion forces. So when our forces, though, are comparable, the solution is made. Okay, the substance dissolves. All right, now let's talk more about each of these steps that's kind of occurring in this picture. Oh boy, that's the arrow. I need my marker. Okay. A solute dissolves in a solvent because the solute solvent, so the interaction between the solute and the solvent, that attraction that says overcomes. It overcomes the solute, basically the attraction that's keeping the solute together, that attraction, and it also overcomes the solvent-solvent attraction. Okay, it overcomes both. If we look back at that picture, the salt dissolving picture, the solute attraction was the ionic attraction, and the solvent attraction was the hydrogen bonding. Okay, the solvent attraction was the ion dipole. So, in essence, in that example, the ion dipole attraction is stronger and overcomes both the solute attraction and the solvent attraction. Okay, it has to overcome both. And I know what some of you might be thinking. Well, Mr. Markey, did you just say the ion dipole is stronger than ionic? Well, no, I did say that, but it's not. We have to look at one other aspect of this. So if you're thinking that, good thought, because that's kind of the problem. It's like, hey, how can that actually happen then? There's something else that also causes a solution to form. We'll kind of get into that here in a quick moment. Okay, so it's kind of like a three-step process here. So, oh boy, that says think. We can think of the overall energies of the solution formation as having three components. That does not say components. Components. Sorry. All right, delta H. We have our delta H of our solution. All right. So the entire change in enthalpy, change in energy of our solution is going to be equal to the delta H of the first process plus the delta H of the second process plus the delta H of the third process. Okay, it's a three-step process. Okay, I'm going to go over what each one of these processes are here in one quick moment on the next page. All right, I'm going to draw some images here, so bear with me. Let's look at each component of our solution individually. So let's say we have here a beaker of our solid solute. You can think of it as NaCl if you really wanted to. I'm going to make my, I can't make it white because that won't really show up. Maybe it will show up. No, you can't see that. So no, I'm not going to choose white. Let's just choose black. So here's our NaCl, right? Our sodium chloride crystal, solid crystal, locked together, very close together in a crystal lattice, right? Sitting at the bottom of your beaker. Yay. Cool. Now, in order to dissolve that, it has to separate. You have to basically, just dropped my pen. You have to separate each of the ions from each other. So you have to break down the crystal lattice structure. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, cool. So you break it down, right? This is our solid solute. We could call this delta H1. This we are referring to is the separation of solute molecules. Okay? So since we're separating molecules, since we have to overcome the crystal lattice, we have to overcome the ionic forces between those two ions, this is always an endothermic process. This is always going to be requiring energy. You have to add energy in to do this, to separate those ions. Okay? Now the other thing we have to separate is the solvent. Okay, so let's say here we have our solvent. I guess if I'm going to make it water, I'll make them blue. So here's my liquid, right? Liquid molecules are relatively close together. They're spread all over the place. Yay. Okay. If the liquid, right, if the solvent is going to dissolve the solute, it has to make room for it. Okay? They have to spread out. So I'm going to try to demonstrate this. So these molecules are going to have to spread further apart and have little spaces between them that weren't there before. Okay, if we're using water as our example, then the hydrogen bonding is going to have to be broken down. Okay, you have to move and separate these H2O molecules from each other, whatever your solvent is, doesn't matter. We could call this delta H2. This is the separation of the solvent molecules. And the same as before, since we're separating and breaking down hydrogen bonding, if water is our example, we have to break down whatever force there is in our solvent. This is always endothermic as well. This requires energy. Okay? So these two things, when you dump salt into water, these two things have to occur first. Okay? The ions get separated, and the H2O gets separated to make space. And we have to look at delta H3. Delta H3 is basically the combination of all of this. Okay? We have our separated ions. 2 and 2, 3, 4, 5, 6, 7, 8, yay. And we have to add, that's a terrible looking plus sign, oh well. We have to add our separated water molecules, or solvent molecules. Okay? Those two things combined create our solution. So there's all the H2O, and I'm going to add the black salt molecules. That's probably more than 8. Oh well. There's our solution. Okay? This we call delta H3. The formation of our solute solvent interactions. Okay, since we're forming new interactions, we're forming new intermolecular forces, forming interreactions releases energy. This is always exothermic. Okay. So if you guys look at the signs of these delta H values, right, in order for a... Actually, no, 1 second. Yeah, I'm going to do this. For a solution to spontaneously, we've seen that word before, to spontaneously form, that looks like farm, it's supposed to say form. So for a solution to spontaneously form, delta H of the solution must be exothermic, meaning it has to be negative. Okay? And since delta H3 is the only value that's going to be negative, your delta H3 better be large enough, a large negative value, to overcome the two positive values that are delta H1 and delta H2. Okay? If that happens, then your solution will form spontaneously. Okay? Here's a little diagram I can share with you guys. I found this diagram in one of my textbooks that kind of summarizes these two ideas. Basically, one idea being if your delta H of your solution is negative, and one idea is that what if your delta H of solution is positive. So it just kind of summarizes up the ideas, puts it into a graphical form. You guys could pause the video here really quick and copy it down. You could keep going and come back to it. You could look it up later. It's online. It'll be posted to the website and copy it down or study it on your own. but I thought it did a pretty good job of kind of outlining what's going on here. You've got an increase in enthalpy here on sort of like your y-axis, so to speak, going up. So here's our delta H1, right? Delta H1, you have to add energy in, right? So you have your solvent plus your solute. First thing you have to do is you have to separate your solute particles. Okay, that's your delta H1. Then delta H2, you have to separate your solvent particles. You have to add energy for both of these things to occur. So once you get them both separated, they're going to combine, and delta H3 occurs, and that releases energy. Okay, if you release more energy than you put in, then you are exothermic. The net exothermic process is your delta H of your solution. Okay, you are lower in total potential energy because you have released some. Now the exact opposite occurs over on this part of the diagram. Okay, so here you have your solvent and your solute. Delta H1, you have to separate your solute. Taking a look at the size of the arrow, that takes quite a bit of energy. Delta H2, you have to separate your solvent, adding more energy. Then, once they're both separated, they can combine, and you get your delta H3, releasing energy to make your solution. But notice that this did not release enough energy to actually bring it below where you started. So, this is a net endothermic process. To make the solution, energy would have to be added in. Quick side note, what would the solution feel like if it's endothermic? Pause. All right, continue. It will feel cold. All right, these solutions feel hot. All right, there's some really good examples of that that I obviously can't do for you guys because I'm not there. But remind me and I'll do them for you. They're really neat, really highly exothermic solutions and highly endothermic solutions. Pretty neat. Okay, like I said, you can come back to this, take a look at it later on if you want to, copy it down, maybe go back, pause it, leave it up there on the screen, and copy it down later. But we're going to move on to the other idea that has to occur, right, for these solutions to be made. Hey, if we can make a solution and it's endothermic, well, that's not spontaneous. How does it happen then, right? Sort of like what we said before. Mr. Markey, ion dipole forces aren't stronger than ionic forces. Well, then how are they supposed to pull them apart? How is that energy supposed to have enough energy to pull apart the super strong ionic forces? Because there's another factor at play here we have to recognize. So let's take a look at that really quick. It's actually pretty simple. Okay, so the other, there's the arrow again. All right. Oh, why? No, I meant, there we go. Okay, another factor is what we call disorder. Okay, so disorder is something we look a lot more at later on, like chapter 20. But spontaneous processes occur when they become more disordered. Disordered. Another word for disorder, random. So, kind of a blanket statement right here I'll start to make and stress much later on in the year. Naturally, things like to become more disordered. Okay, things do not like to be ordered. Atoms, elements, molecules do not like to stay ordered. If they find a way to become more disordered, they tend to do that spontaneously. Okay, so looking back at our example, right, we had a solid solute that was organized. It's in a solid crystal lattice structure, very, very organized, repeating structure. That's highly ordered. When you dissolve it, you break it all apart. You spread all the atoms and ions out into a solution. Very disordered, super messy. Okay, that happens spontaneously. So, formation of solutions, that looks like farm again. I need to stop doing that. Formation of solutions is favored, oh boy, is favored by the increase in disorder. That occurs from mixing. So, back to that sort of original question, how can you make a solution that's going to be endothermic and therefore non-spontaneous? Well, it's because of the disorganization of all the solutes and solvents. If they're becoming more disorganized and more chaotic and more random, that actually pushes the solution formation forward. And the solution forms spontaneously, even though it's absorbing heat energy. Okay? So that's kind of like the other factor of solution formation is the disorder. If you see something becoming more disordered, more disorganized, more spread out, that all means spontaneous. Okay, one last topic we'll discuss in this section, and that is solubility. All right. Now this section should contain a lot of terms that you heard from in your first year chem class or even earlier. So make sure you access that part of your brain that tells you what these words mean. Because we'll kind of describe them in just more of an intelligent manner. All right. So we have to recognize that as a solute dissolves, its concentration increases. Makes sense? But as your concentration increases, so do the number of collisions. More specifically, so do the collisions of the solute particles with each other. So again, using salt and water as our example of our solute and solvent, if you dissolve NaCl, your solute, into water, it starts to dissolve, increasing its concentration in the water, but then as all those atoms and ions are moving around, you might get a sodium and a chloride to collide back together and form the solid again. Not entirely impossible when you think of the total number of ions floating around, and there are trillions upon trillions upon trillions upon trillions of them. It just, on our level, it tends not to happen enough that we see it form, right? But it does happen. If enough of them collide, well, then you do get the solid back. We call this crystallization. Basically, the opposite of the solution process. If the solution process is dissolving a solid, then the crystallization is actually getting the solid back. The solid solute crystallizes out of solution. We can represent this idea sort of like an equation. If we have our solute and we mix it with our solvent, then those processes go together and they form our solution. And they do that by dissolving. Okay, but we could also go backwards. Okay, and backwards we would call crystallization, or it would crystallize. So our solution should be able to become separated, right? I want you guys to understand that we're not talking, throughout this entire chapter, we're not talking about reactions. We're not talking about anything being reacted, okay? When you react something, it's very sometimes impossible, but very difficult to get that reaction to run backwards, okay? But with making a solution, you should be able to separate the particles out, all right? You should always be able to wind up with your solute and your solvent separated back out if you wanted to, all right? So again, the silly example, salt and water, right? So you have NaCl, which would be your solute, water would be your solvent. Mix those two things together, the salt dissolves, you get your solution. Well, as I said before, you guys know that if you let the solution sit out, the water evaporates, and the solid salt crystallizes, and you get both things back. You have your solute, your salt would be left in the cup, and your solvent would actually be now water vapor, I suppose, but it's separated, right? All right, that's the idea. Now, these two processes occur simultaneously, all right? They both occur at the same time. Oh, geez, there's my arrow. So, when these two rates of opposing processes become the same, no further increase in the amount of solute in solution occurs. Amount of solute in solution occurs. So again, both of those processes are happening at the same time, right? As soon as you put your solute into the solvent, the dissolving process occurs almost 100%, majority, everything. It's always constantly dissolving. But as more and more dissolves, that means more and more of those particles can collide and then crystallize back out. Okay? Once those two rates, all right, become exactly the same, you can't dissolve anymore. Okay? Your dissolving rate equals the crystallization rate. Okay, and we have some terms you guys should recognize. The term we call for this is a saturated solution. We say it's saturated. All right, simple definition, no more solute, can dissolve. Okay, basically the sentence up above is describes a saturated solution. Okay, so when the two rates are equal, when you cannot dissolve any more, you say the solution is completely saturated. Okay, and that brings up our term solubility. Solubility. Okay, solubility is basically the amount of solute needed to form a saturated solution. And it's always in a given quantity of solvent. So we state solubility as the amount of solute that you can dissolve in a given amount of solvent. Okay. So usually this is expressed as a gram amount. It could also be expressed as a molarity. Here I'll show you an example. So just a specific example, the solubility of NaCl in water at 0 degrees Celsius, temperature has to be stated. Solubility of NaCl in H2O at 0 degrees Celsius is 35.7 grams per 100 milliliters of water. Okay, so you have your mass amount, right? The grams of your solute per your amount of your solvent. Okay, and again, a temperature is always stated because solubility does change with a changing temperature. So technically, you can dissolve more of something like salt in your water when you jack up your temperature. Okay, and again, this is an idea discussed that you guys learned about back in your first year chem class. So definitely make sure you guys are familiar with the whole idea of solubility, and I'll add a little note here. This value can be represented as a molarity amount. So if we wanted to, we could convert our grams of NaCl into moles, divided by our amount of water, things like that. Our liters, of solution. So we can represent solubility as a molarity. Either one works. Okay, now this idea of saturated, right? We also have the idea of unsaturated solutions, and I know you guys all know what this definition is. Basically, you have your solution, and it still has the capacity to dissolve more solute. Okay, so unsaturated means you can still dissolve more. Saturated means you can't dissolve any more. Okay, you could, so for example, we know that 35.7 grams of salt will dissolve in 100 milliliters of water. Great. I measure out 100 milliliters of water exactly. I'm at 0 degrees Celsius. Also ignore the fact that 0 degrees Celsius means water's frozen. Just ignore that. Anyway, don't worry about that. Okay, so I have 100 milliliters of water exactly, and let's say I dump in 5 grams of NaCl. Yay! I would have an unsaturated solution because I still could dissolve more. I could dissolve 30.7 more grams. Great. So I dump in 30.7 more grams for a total of 35.7 grams of NaCl in 100 milliliters of water exactly. Great. I would then have a saturated solution because it can dissolve that much and no more. But let's say I go crazy. I keep dumping in more. I dump in 14.3 grams more for a total of 50 grams dumped in there. Well, guess what? I still have a saturated solution, and I've only dissolved 35.7 grams. That's all it can dissolve. The extra 14.3 grams that I dumped in just float to the bottom, and they sit there as a solid, undissolved. Okay, so you can keep dumping in more and more of your solute. It's not going to dissolve as long as we keep our temperature constant and our amount of water constant. You guys are familiar with the ideas that if we start changing those things, the solubility changes and how much you can dissolve changes. Okay, now, one last little definition. I know you guys are waiting for it. Jeez. If we have our unsaturated solution, it is possible to have a supersaturated solution. Very cool. This is a solution that contains a greater amount of solute. Than what was needed to make a saturated solution. Cram the word solution in here. These types of solutions are very unstable. Okay? So supersaturated is all about dissolving, actually getting to dissolve more than what you should. All right? So back up at our solubility example up here. Just so we're clear, if I dump in 50 grams at 0 degrees Celsius in 100 milliliters of water, I will not have a supersaturated solution. Dumping in 50 grams means only 35.7 will dissolve, and the extra 14.3 will just sit at the bottom. That does not make a supersaturated solution. Supersaturated means you have to get it all to dissolve. So we have to do something special. Something like salt doesn't really form, table salt anyway, doesn't really form supersaturated solutions, but some substances do. So let's take a look at the conditions we need to have to make a supersaturated solution. Okay, I've got some diagrams here we'll be looking at in a quick moment. So we have to understand this very nice idea is that more solid solute dissolves at higher temperatures. Okay. In this example, this is sodium acetate. Okay, NaC2H3O2. Sodium acetate readily forms supersaturated solutions. It's kind of neat stuff. If we take a look at this solubility curve here, it says here we have the solubility of sodium acetate. We've got temperature on our x-axis, and we have the solubility per 100 grams of water on the y-axis. And so this line right here represents how much sodium acetate you can dissolve in the 100 grams of water over different temperatures. You'll notice that it increases as your temperatures get higher and higher. Okay, that line represents a saturated solution, right? The solubility of it. If I dissolve less down here, so let's say at 50 degrees, I only dissolve about 50 grams, I would then have an unsaturated solution because I still, at 50 degrees, I could actually potentially dissolve somewhere pushing 100 grams. Okay, so that would be unsaturated. If I somehow manage to dissolve over 100 grams at 50 degrees Celsius, I would have a supersaturated solution. So in a solubility curve, unsaturated are always below the curve, supersaturated is always above it, saturated is always the curve. A quick little side note on those graphs. And those do pop up sometimes on the AP exam, graphs like this, and they ask you different questions about it. In order to make a supersaturated solution, what we have to do is we have to heat it up. Okay? Sorry, I'm going to pause writing. So let's say, for example, I heat my water up to 100 degrees Celsius. No, that's crazy. Let's do 75. We don't want to boil it. So let's go 75 degrees Celsius, heat it all the way up to 75 degrees Celsius. I should be able to dissolve, this looks like approximately 10, 20, 30, 120 grams. Okay, so at 75 degrees Celsius, in 100 grams of water, I should be able to dissolve 120 grams of sodium acetate. Whew, that's a lot. Okay, and I get it all to dissolve, right? Perfect, make a saturated solution. But then I slowly let it cool. And as I let it cool, I move this way along the graph. I become now super saturated. As it cools down, let's say I let it sit overnight, the beaker then will cool down. I'll let it cool down to room temperature, let's say 25 degrees Celsius. Actually, our room is going to be colder, probably somewhere around here. I wonder if the room is still cold. I don't know. I haven't been there in a while. So we would be somewhere right here. Okay, and I will now have dissolved, still keeping 120 grams dissolved in solution. But I shouldn't be able to do that, but it does. So, let me get my pen. If the solution is slowly cooled, it's possible the solute remains dissolved. Now, not all substances do this. Sodium acetate is always the classic example that gets used. So what's really neat, and the picture on the left shows you, in order for crystallization to occur, the molecule or ions, the molecules or ions must arrange to form crystals. There's one more point I want to make, but I want you guys to take a look at the photos here. Now, these photos I'm pretty sure are in our textbook. I grabbed these from another textbook. You can look it up. They're pretty widely used photos. It's a widely used supersaturated example. Here, what looks like a nice homogeneous solution. But it's crazy the amount of solute that's dissolved in here. In fact, most of this right here is dissolved solute. It's crazy. It's not actually water. A very small amount of this is actually water, but it looks like it. Now again, you guys probably should have, anyway, your chemistry teacher probably showed this to you in your first year chem class. So what we do is, in order to get the extra solute to crystallize out, we drop in one single tiny little crystal of solid sodium acetate. And as soon as you add that to the solution, it starts crystallizing. So here you see the crystals start to grow. It's a really neat process. And now here you can see actually what all was solid solute. Most of the beaker was made up of solid solute, but it remained dissolved. Really neat. Again, take a closer look at the images in your textbook or look it up online. Do sodium acetate supersaturation. Probably see lots of videos of it. So let me write down the last point to the supersaturated idea and let's wrap up. Okay. Oh, geez. So, adding a small crystal. That small crystal is what we call a seed crystal. So add a small crystal provides a template for all other excess solute to crystallize. All right. That was the last point I wanted to make. A good term to know is this idea of a seed crystal, is what we call it. That one little teeny, I'm talking like you can make it literally just molecules. And if you introduce that to the supersaturated solution, all the rest of the solute particles see that model of the crystal lattice, and they start to all realign to form the repeating crystal lattice, and then they all crystallize out. It's It's really pretty. But it's a very small amount that you have to just dump in. Okay, and sometimes even knocking them together, like the supersaturated solutions I said are very unstable. When you carry them around, sometimes just knocking them very hard, you actually align some of the crystals, and it all starts to crystallize out. Neat stuff. Definitely look up a video of that if you guys don't remember seeing that one from your first year chem class, or if you never saw it. Okay, that's the first section. Definitely read through some of those main ideas in our textbook, get a better idea of it, re-look up ideas. If you're not fully understanding them, you can find lots of practice problems and material. The questions I picked out are really good questions to be able to answer and describe and explain. Don't go for simple explanations. Really get deep down and understand things on an intermolecular forces and on a very small molecular and atomic level. All right, next time we'll look at things that can affect the solubility and a little bit more details on solutions.
Made with Doodlecast Pro.